Welcome once again, students, to the microwave spectroscopy at Benchtop Chemistry. So far we had been discussing about the basic principle of microwave spectroscopy, and there was an approximation that we learned on the last turn, that means in the last previous video. And we studied that when we deal about this particular spectroscopy, there was an approximation. And what was this approximation? The approximation was that we are considering a rigid molecule. We will be talking about the diatomic molecule, which is actually rigid in nature. Okay, so this was the approximation that we had mentioned in our previous video about the rigid molecule. Today we are going to learn into detail more of the molecular rotations. So for that sake we need some of the assumptions. So let's move further with the assumption. So we assume, before moving on further, we assume that we have point masses. So usually we assume the point masses. Let me name the point masses as m1 and m2. Okay, and these point masses are separated from one another by means of a particular distance, that is called as bond distance, and they are lying along the bond axis. So this is our first assumption over here, that we are taking point masses. Okay, so I'll just draw the point masses over here. This is my m1, okay, and this is my m2. So m1 and m2 are the point masses, and they are separated from one another by the bond distance, okay, which we call as bond length. And this is the bond axis, the axis along which the masses are lying. Okay, so this is the bond axis. Okay, we also assume that the molecules undergo genuine rotational motion. So the second assumption is that genuine rotational motion of the molecules is taking place. Now, what is genuine rotational motion? Which means actually that the molecule itself is not moving here and there. So this entire molecule over here, which I have drawn, which consists of m1 and m2, two masses, two atoms, this entire molecule is not moving here and there. So it is in its position only. So since it is not moving here and there or away from its own position, so what happens, actually the mass of the molecule does not move away. So when the entire mass of the molecule is not moving away, the center of mass remains where it is. Okay, so that is the reason the center of mass remains where it is. So here, so this Cm marked over here, actually it is the center of mass of the molecule. Now since the molecule is not moving from its position, it is not moving here and there, we are only considering the rotational motion of the molecule. So definitely when the molecule is not moving from its position, so we consider the rotation, all the rotations along about the Cm, about the center of mass, are considered, about the axis passing through the center of mass. And this is the axis which is passing through the center of mass, which is also called as the bond axis. Okay, now we keep this in mind that Cm does not move. Cm is not moving over here. Okay, now let's focus upon the different axes which are under the consideration. This line in gray color, let me assume that it lies along the x-axis. So definitely if I consider this axis, which is the axis passing through the Cm, or the axis passing through the bond axis, okay, so the rotational movement about this axis will be considered, and that, let me say, I mark the moment of inertia along this axis as Ia. There is another axis also which lie perpendicular to the bond axis, right? And the rotations along that particular axis, if we consider them, I'll mark it like this. Okay, so if we consider this axis, which is, let's say if it is the y-axis, all the rotations around this axis, I'll label the moment of inertia along that axis to be as IB. And the third axis, which is actually perpendicular to these both, the x and the y axis ones, this is perpendicular to the two others, that the rotation along that particular axis are also considered. Okay, and I mark the moment of inertia along this axis as IC. So therefore we discuss the rotational motion of these point masses now about these axes. Okay, now if I say that the distance between the mass 1 and the center of mass, okay, that is cm, it is, let me say I label it as r1, right, and the distance between the cm and the second mass, that I label as r2. Okay, so if the distance are r1 and r2 with respect to center of mass, so the moment of inertia, which I label as I, is equal to what? It will be equal to, since the body is containing two masses, it will be m1 r1 square plus m2 r2 square. This will be the moment of inertia of this molecule. Now actually, since the I is the moment of inertia of the molecule, that is represented over here, and this is about an axis passing through the cm or the center of mass and perpendicular to the bond length. Now the perpendicular distance from the cm or from the bond axis actually happens only to the two axes which are perpendicular to the bond length. Okay, and it is all those two axes, these IB and IC, carrying the respective two axes, along the respective two axes, these are identical in both the cases. So R1 and R2 is will be standing as 0 for the bond axis. That means if I am talking about this bond axis only, R1 and R2 will be 0. Okay, so in that case along the bond axis, if we are asked about the moment of inertia, we say that I is equal to 0. However, it is not exactly 0. It carries a very small value. Why? Because we cannot ignore the two masses. Okay, so but yes, we assume that I is equal to 0 about the bond axis, as the relative position of the particles, it does not change. Okay, now this is the moment of inertia. If we talk further, if we take this particular expression further into more detail, let me say that m1 r1 is equal to m2 r2. Okay, and this is the case when we talk with respect to the center of mass. Okay, so that means at center of mass, that means at cm, which is marked over here in the figure, m1 r1 is equal to m2 r2. Okay, now since m1 r1 is equal to m2 r2, so that means we can expand this, our first expression, further. How? Let me see. m1 r1 moment of inertia is equal to m1 r1 square plus m2 r2 square, right? So I can, if I just try to make it simplify, let me say I just expand this. So I can write m1 r1 into r1 plus, and I can also write it as m2 r2 into r2. Okay, so I've simply expanded this r1 square and r2 square. Okay, now since we know that from this particular equation m1 r1 is equal to m2 r2, so I can write this much part of the expression as m2 r2. Okay, and then it is into r1, right, plus, now this much part of the equation I can also express it as m1 r1 into r2. Okay, just simply substituting those two terms. Okay, now from this particular expression I can see that on both the sides of the plus sign, r1 and r2 are the common terms, so I take them out as common, and what will be left inside? m1 m2 plus m1. This is m2, this is m1, so this I get over here. Okay, now this r1 and r2, R1 plus R2, I take it as R. Okay, so considering R1 plus R2 is equal to R, we will try to expand this equation further. How do we go? Let's see. So I can write as M1 R1 is equal to M2 R2, which is equal to, let me say, I write it M2 into R2. I can write R2 as R minus R1 also from this expression. So R2 can be written as R minus R1, and vice versa, R1 can be written as R minus R2. Okay, so now if I try to substitute this part into my equation, I will get M1 R1 is equal to M2 into R minus R1. Okay, so this will be, I am just simply expanding it, opening up the brackets, and let's see what comes with us. We get this equation. We get what we do is we just take this R term on one side and R1 R2 whatever is there in terms of 1 and 2 on the other side of the expression. So what do I get? I get M1 R1 plus M2 R1 is equal to M2 R. Okay, so from this expression I can write R1 is equal to, why? Because on the left hand side I am taking R1 as common, it can come out as common. So this will be equal to M2 R divided by M1 plus M2. Okay, so here from this expression, from these substitution and the values, we get an expression in terms of R1, or let's say in other words we get an expression for R1. Now let's proceed further and take into consideration R2. So up till now we have got these two equations, the main equations that we have got so far. First one is equation A that I have labeled over here, that says I is equal to, that is moment of inertia, is equal to R1 R2 into M1 plus M2. And the second equation we got is equation number 1, which is for R1, which is equal to M2 R upon M1 plus M2. Now similar to this R1 expression, we are going to get another expression for R2. How will we do that? Initially for deriving this equation 1, we had substituted the value of R2 in terms of R. Now we will be doing the same thing in terms of for the R1. So what will we do? It will be M1 into R1 will be what? R minus R2, which is equal to M2 R2. Okay, I simply open up the brackets, M1 R minus M1 R2, it is equal to M2 R2. Now I take both the R1 R2 terms together on one side. So M1 R is equal to M2 R2 plus M1 R2. Okay, so from here M1 R is equal to R2 is common in both these terms into M2 plus M1. So my R2 will be equal to M1 R upon M1 plus M2. Okay, this is the equation that I get for R2, and I'll write this equation over here. So our third equation that we have got is R2 is equal to M1 R upon M1 plus M2. This is our equation number 2. Okay, now what we do next, we simply substitute these R1 and R2 terms that we have got from the equation 1 and 2 into equation A, which is our parent equation. So let's do the substitution part now. So I is equal to R1 into R2, and what is R1? It is equation number 1, which is M2 R upon M1 plus M2 into R2. I need to substitute the value of R2, which is equation number 2, which is M1 R upon M1 plus M2. Now this is to be multiplied by M1 plus M2. Okay, so we get this equation after substituting the values of R1 and R2. Now from looking at this equation, you can simply say that this M1 and M2 can get cancelled by the numerator, in the numerator and denominator itself. So my I will be equal to M1 M2 R square upon m1 plus m2. Okay, so this will be the value of moment of inertia after these common terms get cancelled with each other. Now having a look at this particular expression, if you keep, I just take out this r on one side so that it becomes simpler for you to understand. Can I write this equation as m1 m2 upon m1 plus m2? This I take in brackets and r square. Okay, so I can simply represent the equation in this form also. Now m1 m2 over m1 plus m2 is nothing else but the reduced mass. Okay, so I can write this equation as I is equal to reduced mass, which I represent by mu into r square. Okay, where mu is what? It is the reduced mass. 1 upon m1 plus 1 upon m2, which comes out to be m1 m2 divided by m1 plus m2. Okay, so in this way this moment of inertia can be equated by reduced mass also, or we can say that I is equal to mu r square. So let's summarize our today's derivation. So from today's derivation, we come to know that our moment of inertia of any diatomic molecule, which we have considered as rigid in nature, okay? So the moment of inertia, it is equal to m1 r1 square plus m2 r2 square. And it can also be written as mu r square, okay? Where r is the summation of these distances of the respective masses m1 and m2 from the center of mass, and mu actually is the reduced mass. So this expression is the main expression that we have got today, and we have to keep this expression in mind if we want to consider the energy aspect also in the microwave spectroscopy, because this expression will help us over there also.